Hey guys, it's JM. It's been a very exciting couple weeks in Chia. There's some very exciting new plotters floating around, and I'm going to chat a little bit about what I think this means to the community. I've actually got a fair amount of time testing a few of them over the last few weeks. I've been chatting with a few of the authors on GitHub and in Keybase, so I have a little bit of insight of what's going on. Um, but so one thing I think a lot of people are like blown away that there's some new plotter that can produce a fastest plot in far less time than the previous plotters could. So the current plotter has at this time in June, 23 exabytes that have been plotted with that plotter. So clearly it works. And the approach that they took in the original plotter was one that was a kind of general purpose plotter. It worked very good on hard drives. It worked very good on SSDs, and it really wasn't optimized for in memory. Part of this was because a lot of the phase two and phase three and some of the later phases weren't multi-threaded. It was really you could multi-thread phase one, and that was about it. And so the way to get high throughput or high terabyte per day output on a system was to kind of scale the amount of temporary SSDs, 256 gigabytes per every core. So this new plot is very interesting. This new plotter is very interesting, and I'll talk a little bit about what this means. So in the end, Chia is about proof of space, which just means at the end of the day, the only thing that really matters is the farming capacity, because that's what the plot files on your harvesters and your farmers these are the ones that are securing the network. It's not actually the plotting per se that's securing the network. Plotting is kind of a means to an end. So you have to do it, and so we like plotting to be efficient. The Chia community, everybody should like plotting to be very efficient. Yeah. Now, ideally, you want writing the actual plot file to the final destination disk. Ideally, you want that to be the actual bottleneck. Um, Now, there is some weirdness. If you can complete phase one in under 30 seconds, this is where it starts opening the door to something called a replotting attack. It is defined in the consensus paper, and it has a little bit of insight on why this might not be such a good idea. Not necessarily because we don't believe, or the Chia team and Bram don't believe that it can be pulled off someday, is that it may not be very economical to do. And we're actually going to talk quite a bit about this next week with the Chia team. We're going to do a public Zoom in which we kind of describe the economics of this attack. But just so is it the death of k equals 32? Is k equals 32 over because people can do a plot in 15 minutes or less? No, actually not. That's actually a good thing so far. Fast plots are very good. It's just when another 20 to 30x speed up, to phase one, and we might be in a spot where the team has to. There are some knobs that can be tuned in the Chia protocol to kind of alleviate some of these concerns, or just make this attack less economical. Right? The attack vector is something where it kind of describes it in the consensus paper, but you get a challenge, and then you basically know the plot filter. So you basically only are trying to generate a plot on the fly that passes the filter, that is a response that has a valid proof to that challenge you just received. Now, when a regular farmer, when you have a plot past the filter, you have about 30 seconds or so, about 3 signage points, before you actually have to, get this plot, back to the network to get the proof back to the network to claim your reward. And so this is kind of the time frame which you have in this window, which is to write. Today, a k equals 32 requires 1.3 terabytes of writes. And even phase one is, if you're completing phase one, it'd be about 576 gigabytes of writes, and 256 gigabytes of temporary storage space, kind of the maximum. So this is a lot of data, and so people don't understand this. Even if there were some major speed ups in very highly multi-threading this type of phase one, it's still a very hard problem from a bandwidth standpoint. Not impossible, but very expensive to do. And so most likely people will just remain on the standard what people are doing today, which is storing plots, because that's going to be the cheapest and most economical thing to do for Chia. But that's not the topic of this video. This topic of the video is all about the new plotter. And so the one I'm actually checking out is this one called the madmax. And this is cool. It's been very active. It's being actively developed. You can see 4 hours ago on some of these commits. I mean, it's being very, very actively developed. So the one thing, what does this do? It's not like it is a rewrite in the sense that all the libraries that were required for the Chia proof of space are all used in this. It's just being called in a different way to basically pipeline the plot creation into something that can be very multi-threaded, and that's very good, right? Because one of the problems was that phase one was multi-threaded, but the other phases weren't. So people were doing these staggering and all this trickery to try to get the maximum terabytes per day output on a system. So this fixes that. The second thing is I mentioned that the actual amount of data written in a K equals 32 is still 1.3 terabytes. Now, if your plot completes in 15 minutes and instead of hours, this is like 1.6 gigabytes a second or so average bandwidth, average write bandwidth to the drive. So you still need a high TBW SSD if you're going to do this on an SSD, or else you wear it out. Like, no question about it. And check out the endurance page. But now the very interesting thing about this plotter is that they have a temp 1 and a temp 2, but they're slightly different than the temp 1 and temp 2 in the regular plotter. The temporary one in this directory for this new plotter is 220 gigabytes required, and he says about 25% of the writes go to this temporary directory. I believe some of our community members have actually tested the percentage and the number of writes, and indeed, this temp 2, the majority of 75% of the writes go to. So the idea is that this temporary 2 directory, which is about 110 gigabytes today, this can be a super high TBW media type, like Intel Optane or SLC NAND, or even DRAM. You can make a temporary RAM drive. You can make TempFS and make a RAM drive. Now, 110, or you buy DDR4 and 128 gigabytes. That's actually much more economical than buying dozens of high capacity enterprise SSDs. So on mid-range systems like 8-core, 16-core, this is going to be a very, very interesting solution. I am testing it on some servers too, and I'm seeing lower output than I was on major with a large number of SSDs. But yeah, I still got to do some more testing. So I'm going to go walk through some of the testing that I've done on these, and yeah, I think the key is that on systems that were already optimized, there may not be a high value as far as improving the TB per day output of the system, but you may be able to achieve a similar throughput on a system for plotting on a much lower cost because the economics have changed, and now you can multi-thread all the phases, and now you can get away with a lot less temporary storage space. So this is a very good thing. And so I'm going to show you real quick how to compile this on the Rocket Lake system that I have, and then I'm going to walk through some of the other details on some of the systems that I have. Next, I'm using the bleeding edge kernel. Whoops. Yeah, I'm using the 5.11 kernel. This is like Ubuntu 21. So yeah, there may be some weirdness that I'm seeing here because I'm using kind of the brand new release version of Ubuntu. But what you would do is you would say git clone and then the repo, and then you're going to change directory into that. If I can type today. And then here on, it gives you some instructions of how to install. I'm on Ubuntu, and so I'm just going to do this git submodule update init. This grabs all the submodules like the Blake 3 and BLS. These are the way that the BLS is the signatures that Chia uses for the cryptographic signatures. Blake 3 is the crypto algorithm that's used for the plots. So it grabs those, and then let's see what else we need. You basically have where were we? Ubuntu. You need some dependencies. So you need libsodium, libgmp3, and cmake, and T++. I already have these, but I'll just show you what it would look like. And so we're just going to install all these. It's going to say, yay, nothing new to install because I already have them. Okay, and then so I'm going to go here into the folder, and I'm going to change directory. Well, okay, I go make the development version, so make dev1.sh. It's going to compile pretty fast here. This is a speedy system, so okay. And then all you do is change directory into the build, and now we're going to run a command. So when you run this command, you have to give it, you can see here, it has slightly different format than the standard plotter, but it's real similar. And so what I'm going to do, I already have, believe I already have one that I can steal for this. Okay, so I'm going to give it a screen called plot so I can run some stuff in the background. And so you need a pool key and you need a farmer key. Let me make sure I can see, make sure you guys can see this. So pool key, farmer key, and then you have a temp1 and temp2 directory. I'm just going to put them to the same drive. This is my Optane drive. I'm going to give it 512 buckets. This is the cool thing about this. You can actually give it a higher bucket count than you can in the standard plotter. See how that works out. I'm going to give it 8 threads, and I'm going to run this. Okay, so it's going. And now if I do a dstat here, I can see, you can see here this Optane drive writing very fast, right? About 3 gigabytes a second here. And that's it. So this is running. I'm going to cut over here and show you guys some more about some of the systems I've already ran this on. I suspect this system will be very fast, but the interesting thing about this code is it takes advantage of high core count systems. So this is only an 8-core system. It has very high single core frequencies because it's this Rocket Lake system. So I think it'll perform very good for an 8-core system, but I suspect these other higher core count systems will significantly outperform this. So yeah, now let's cut over to checking out some of the systems I benchmarked this on. All right, so I've had a chance to test out the madmax on a few of my systems. The first one I tested it out on was the Dell R740 XD. That was the system that I had written an article about on Chia Central, just testing out some different drives, the Intel drives, and I've tested out some WD drives on that. So that system out of the box was getting about 8 terabytes a day. This is a dual 22 core system with 256 gigabytes of DDR4. And I had that in here in the sheet. This was our community spreadsheet that, for better or for worse, is hosted under my personal Gmail account. At some point we need to get that switched over to the rest of the Chia team. But yeah, this has two Xeon Gold 6152s. These are 22 core CPUs, and I've got 256 gig of 2666 LR DIMMs. So the system that I've got about, it's very CPU bound. I've thrown different types of SSDs in there. But basically on any of the NVMe SSDs, I get about 47,000 seconds per plot. And that's not great for a single plot, but it's using just one thread and it's doing 44 of them in parallel. And the system's getting 8 terabytes a day. So that's not bad. I'm sure we've had some other dual 16-core systems that I pushed up to about 12 terabytes a day with fully tuned, and that's the topic for another day, I guess. But so for madmax, I created a new tab over here, and I've taken that same system and I've ran it a couple different ways. So I have just one Optane SSD in there. It's an 800 gigabyte P5000X. And then I've done some testing using TempFS, using a RAM drive for this Temp2, and I've also done one just using the P5000X. And then, so you can see here in the spreadsheet, it's very similar as the other one. Instead of parallel plots being a high number, you just have the parallel plot being 1, and then your plot time is much faster, and then your TIB per day output is over here. And so out of the box, actually, it's funny. I think the very first run I did on this was actually the best. I believe I tested, 512 buckets and 128 buckets, and the 512 buckets on the Optane and TempFS actually did perform better. Then slightly, it wasn't a huge difference. I think the 128 was here like 1500 seconds, and so I got 1300 second plot time. 21 minutes, and 4.6 GIB per minute. And this is, 6.54 TIB a day. So this is less than I was getting on the system optimized before. This is actually, so this is saying using madmax on the system, I get 6.5 terabytes per day versus 8 terabytes per day. Sorry, my cat's trying to eat some bad things. Cat. Okay, say hi to the camera. Everybody loves you, Moxie. Okay, stop eating my cardboard. Okay. Yeah, the surprising thing was the Optane drive, just using Optane for the Temp 1 and Temp 2, was actually the same performance as a RAM drive. This is really shocking. So this Optane SSD has 100 drive writes per day, or I think somewhere around, I think it's like 72 petabytes written or something absurd. I can actually here click on the link. You can see here in the Intel website, 100 drive writes a day is the endurance rating for these drives. So this is a super high endurance drive. So this, if you can get the 400 gigabyte version, maybe cheaper. Maybe if you find it through 75 gig Optane, if you can find it for $1 a gigabyte, this might be cheaper than the 120 gigabytes of DDR4. So it's interesting to look at. And then so I tested this Dell system a couple times, and yeah, this 1300 was the max I got. One of my Intel colleagues was testing the same drive on one of the new Ice Lake systems. I am still waiting to get my hands on Ice Lake server. I've put an order in for some about a month ago and still haven't got them yet, but I can't wait. I'm very excited. But he's got one, and he's produced a plot with madmax about on like 860 seconds with this same drive. So wow, that's really fast. Yeah, and so if you could even see here, if we put in 860 seconds, that would be equivalent of about 10 terabytes a day. That's pretty good. So yeah, there's going to be some very economical systems. I think that was a 38 core system that he tested. And so we'll see some probably very high output. I'm interested to see how well this scales with AMD Rome or Milan with like these high 32 and 64 core systems. Because obviously when you go to more cores, you have to reduce the CPU frequency, and at some point you just you're not going to scale. So the other test I did was on the trusty budget build, because I had so much data on this budget build. Right, this was the one that we wrote the blog about a long time ago. That was about 3 terabytes a day output, 2.8 TIB a day. Was kind of where it landed at with the stock plotter. Depending on if you had just fast enough NVMe storage. And this was using the Asus Z490 Prime, and I got the stable overclock, for this, well, not overclock, but, basically removing all the C states and whatnot, so you can get this i7 10700K. It's all core turbo up to 4.6 gigahertz indefinitely. So this system has 32 gigabytes of DDR4, and I tested it with a 4 terabyte hard drive. So just a WD Red crappy hard drive I had laying around. It's probably some old NAS drive. I had an S4610 SATA SSD. This is the Intel SATA SSD, the high endurance, kind of SATA SSD. And then I tested an 8 terabyte P4510 NVMe, and I tested it two ways: one with 128 buckets and one with 512 buckets. So this was very interesting, and this was actually some surprising results to me. So this is where I've sparked some more interest in additional testing here in the next couple of weeks. So hard drive is terrible, right? Abysmal, 28,000 seconds. It's 8-hour plot time. So I mean, maybe before that was actually, this is probably slightly better than it was on the hard drive on the old plotter. So hard drive plotting possible. It's very slow, but it's possible. And so that's bad. On the total system, you're only getting 0.3 terabytes a day. So on the SATA SSD, SATA SSD is limited to 550 megabytes per second or so on the bus. Yeah, and so there's a huge bottleneck. Even though this SSD has a lot of flash on it, 3.84 terabytes, you can't fully utilize the flash because of the SATA interface. And you get 1.3 TIB a day. You get about 6,498 seconds plot time. So when I tested this, I'm gonna actually go and put. I got to power off the system and throw this Optane, this P5000X. I got to take it out of the server and put it on the system, and test it. See what times I get with 8 cores instead of comparing to 44. But this would be very, very interesting to see. It's clear that this $3,000 server that I have that has two 22 core CPUs and 256 gigabytes of DRAM is probably overkill when I can get very high output on a lower end $700 system, which is this budget build. And so this you don't need an 8 terabyte drive. Obviously, this is just what I had laying around in there. But so ideally, you can have a kind of smaller capacity SLC drive. Now there's some of these drives that do this hybrid caching, where they have SLC and TLC, SLC, dynamic SLC. even the let's see, even the 670p from Intel, the 2 terabyte, I think has like 200 and something gigabytes of dynamic SLC, which uses SLC. Um, you know, when the drive's not that full. So a lot of these drives to have a lot of SLC cache might actually be okay for this 120 or 110 gigabytes of temp space, temp two. Um, and so the problem is not all these SLC caches work the same way. So there's ones like Enemotus, I think, does one of the Fuse drive. They do it properly where it's like an actual SLC drive plus QLC. Same with the the Intel, I think it's H20 as the new one, where they have an Optane SSD, a small capacity like 64 gigabytes or 32 gigabytes, then paired with like a larger capacity QLC. So we'll see. There's some interesting drive combinations. I think that are going to work much better. Obviously, this is not the cost-effective drive here, but what I had laying around. And so I tested this with two different configs, one with 128 buckets and one with 512. And this was very weird results to me because the phase one time was actually better on 128 buckets by a lot. 626 seconds versus 1,000. But the total time was lower on the 512 buckets versus 128. So I haven't really wrapped my head around this yet. I need to dig in of what's exactly happening here. But I suspect that the more random I/O is hurting on phase one, but it's helping on the other phases. With the higher number of buckets, increases the IOPS, and I haven't done the trace or anything. But so yeah, I just said, yeah, this system can be had for about $900, and so this is great. $246 per terabyte per day, 3.6 TIB a day. So this is better. Remember, this system could do about 2.8 TIB a day prior to madmax. Maxed any with the fastest SSDs I could throw at it. And now the system is doing considerably more. So yeah, this plotter seems to be working very well in this budget build. And so with that, I'm super excited. No, this is not a bad thing. No, the Chia team is not freaking out. No, this is exciting. We want to learn more about kind of some of the optimizations that he did. And we've been chatting with him on GitHub and whatnot. And I'm looking forward to testing this out on a few more systems and coming up with a couple configs that I think are going to be the new price to performance leaders in this space. So, all right. Thanks, guys.